In the last video, I've calculated the resistance of a light bulb with this rating. So let me write down this result. So a light bulb with this rating should have a resistance of 881.7 ohms. But what I like to do next is to find a way to estimate the resistance of the copper wire that connects the voltage to the light bulb. Oops. Okay. First, let me clear some space. Okay. So what I want to do now is again to find the resistance, but this time I want to find the resistance of the copper wire. I don't actually have any information on the copper wire yet. What I'm going to do is I'm going to make a reasonable estimate. I'm going to try and make a reasonable estimate. But where do I start? Well, let me start by writing down an equation about the resistance of a piece of material or wire. Okay, the equation looks like this. R is equal to rho L over A. Now let me explain what this means. Suppose that I have a piece of wire or just metal with a long kind of uniform shape. Maybe like that. So this could be, for example, a short section of the copper wire that is magnified. So suppose that the length of this piece of wire is L. So that's L. And that's what the L here means. L would be the length of this wire. And A would be the cross-sectional area, with this area here of the cross-section, or the area of one's end. Now, rho is a constant. Okay, let me just quickly talk about R first. R is the resistance. So that's the resistance as we understand from Ohm's law, right? The resistance that this would offer to a current if you apply a voltage across it. So that's just the resistance. Rho is a constant. Rho is a constant that it depends on the material. Now let me write down the name for rho. Rho has a name. Rho is called resistivity. So it is a constant in the sense that for a given material, like say copper, the value of rho does not depend on the length or the cross-section of the wire. So if we know the value of rho of the resistivity for copper, then we would be able to find the resistance of any piece of copper wire if we know its length and the area. And it doesn't have to be copper wire either. If I have, say, tungsten wire or iron wire or some other wires, that other metal could have a different value for its resistivity. Now, as long as I know that value, I can use that value to calculate the resistance of a piece of iron wire or tungsten wire, for example. So the best way to get to know this is to try out one or two examples. But before that, let me just quickly look at this equation and to point out some of the features of this equation. Now, what we have here is an equation that relates the resistance of a piece of wire to its length and its cross-sectional area. Now, if you look at how these are related, L is on top and A is at the bottom. That means that if L is bigger, if I have a longer piece of wire, then according to this equation, R should be bigger. And that makes sense. If I have a longer piece of wire, if say I double the length of the wire, the current has to go through twice the resistance. So I would expect that the resistance is doubled. Now conversely, if I double the area, one way to think about that is like having an additional wire in parallel. Right? Doubling the area is like having another piece of this wire in parallel. So that would also offer double the area. And if that's the case, you could give the same current two different routes. Okay, so if I have another piece of this wire next to it, you can have half the current going through each wire. Okay, with less current going through each wire, it will just experience less resistance. It's like having water flowing through a thicker pipe, for example. So in that sense, we can kind of understand why L is on top and A is at the bottom. Okay, because if you double A at the bottom, then when you divide by a bigger number, you get a smaller answer. So now let's try some calculation. So first we need to know the value of the resistivity. So I'll start by writing down some typical values. Say that's rho, and if I want to calculate for copper wire, I'll need to know rho for copper, but let me also write down the rho for tungsten, just for comparison. Right? Tungsten is the material used to make the filaments of many filament lamp. So we would be looking at this later as well. Okay. Let me just clarify this a bit. That looks more like an F actually, but what I just want to write down the values of rho, the resistivity for copper, and for tungsten here. Okay. So the resistivity for copper is 1.68 times 10 to the power of minus 8. And the units for resistivity is ohm times meter. Is ohm times meter. Now if you look at it, you can understand why it's ohm times meter from the equation, because from the equation, see that on the left side, the units for R is ohms. And on the right side, the units for length is meter, for A is meter squared. And you really need rho to be ohm meter, because then this meter and this meter can cancel with the meter squared at the bottom, and you get just the units of ohm on the right side, so that it agrees with the units of ohms on the left. Okay, so that's why we need ohm meter to be the units of resistivity. Okay, so let's press on. Tungsten, right? By the way, I looked these numbers up on Google. There are websites where we can find out the resistivity of different materials. If you just Google for resistivity, for example. So for tungsten, the value is 5.60 times 10 to the minus 8, and the units are the same. Okay, but for now I shan't be using tungsten. I'll use that in the next video. For now, I just want to use the copper value to estimate the resistance of this wire. But in order to find the resistance, I also need to know the length and the cross-sectional area of the copper wire. So what is the length and cross-sectional area? That really depends. That really depends on the copper wire. Now I'm just going to make a wild guess. Okay, so hopefully it still gives us something reasonable. I'm going to guess that the length of the copper wire, alright, we have one piece going to the light bulb and another piece coming out. So we are talking about copper wires that would extend from the main socket, for example, on the wall, to say from the part where you switch on the light to the light bulb on the ceiling, for example. And if you think of the size of a room might be a few meters wide, and the lamp might be somewhere in the middle of the room. So I'm just going to very roughly say that the total length of these two wires is about 1 meter. So perhaps it's quite close to the switch. So I'm going to assume that the length is about 1 meter. Okay, so it's probably 2 or 3, but I just want a rough value. So okay, how about the cross section? Now, if you have seen a piece of wire before, you know that it's something that you can hold in your hand, and it's definitely thinner than your finger, unless you're talking about really high power cable that brings electricity to our house. But for household items, we are likely to see cables that are fairly thin. The thick cables that you see, if you would probably contain smaller wires inside. So I'm just going to make a guess that the thickness of the actual copper wire inside the plastic insulation, and what we see and hold in our hands of wires is normally the plastic insulation. So inside that plastic would be the copper wire, and I'm just going to guess that the thickness or the diameter of the actual copper metal in the wire is about 1 millimeter. So using these estimates, very rough estimates, I shall now use this formula to estimate the resistance. Okay, with these estimates, I have values for length, I have values for the cross-sectional area, and I also know the resistivity of copper. That's this number here, which I looked up. So let's Let's try. Resistance is equal to, let me write this out first, rho L over A. That's the formula. But there's one thing, I don't actually know A yet. I know the diameter. I know the diameter of A. Now, I'm taking A to be a circle. So the area of a circle is related to the diameter. If I call that D, the diameter, is related to the diameter by, let's see, area is equal to pi r squared, right? Where r is the radius, and r is half of D. So this is pi times D over 2 squared. So that's the formula we are looking at. So it will look something like that. Rho L over pi D over 2 squared. A little more complicated. But we have the formula that we need. We are ready to substitute 1 meter for the L. Rho are there. 1.68 times 10 to the minus 8 for the rho, and 1 millimeter for the D. Okay, so let me just make this quite clear. So rho is from there. Okay, D is from here. Right, that's the 1 millimeter, which we need to convert to SI units to 0.001 meter. Okay, and L, right, L is from there. L is 1 meter. So this L will go here. Okay, so we have all we need. So now I can use my calculator. Remember to convert 1 millimeter to meters. First, I'm using my calculator. Okay. I find that my answer for the resistance is 0.021 0.02139 ohms. So that's the value of the, I would estimate, of the copper wire. Now let me think about this a little bit. Remember that I have used very, very rough estimates of the thickness and the length. Now if you think about, say, the length, as I said, I'm estimating the length of a piece of wire in a room, right? From the main socket or from your switch to a light bulb somewhere maybe on the ceiling. So we are talking about wires which are probably a few meters at most, because that's the typical size of a room. I estimated 1 meter, but it's more likely to be maybe 2 or 3 meters. So what difference would that make to my answer? If you look at this formula, resistance is related to L. So if L is really 2 or 3 times longer, it just means that the resistance, the value of this answer should be 2 or 3 times more, meaning that instead of 0.02, it might be 0.04 or 0.06. So it's that kind of value. So it might look like it's the actual length would make a big difference. Indeed, it would make a big difference to the answer, but For what I want to do now, it might be alright because I want to actually compare this resistance value with the resistance of the light bulb. If you remember the value that I calculated in the last video for the light bulb is 881.7. If you compare this with the resistance of the copper wire, more than 800 ohms compared with 0.0 something ohms. So the resistance of the copper wire is clearly much smaller than the resistance of the light bulb. So if you imagine a current going through the copper wire and then through the light bulb, as far as the current is concerned, the copper wire offers hardly any resistance at all, right? In fact, nearly all of the total resistance in the circuit comes from the light bulb. And what this means is that for simple calculations, we can usually just ignore the resistance of the copper wire completely.